Good afternoon, everybody, and I'm very appreciative of this opportunity to speak to you about Perl Data Language and the method of the curve fitting used to detect the Higgs boson. I teach an introductory physics lab that's built upon this method, which is chi-square analysis. The lab is called Principles of Scientific Inquiry. And a colleague of mine who I teach with 7 years ago, as a graduate student, went to CERN to do programming on the ATLAS project. A week after he arrived, the Higgs was detected. He claims it's a coincidence. We tease him, we're not sure. But I'd like to talk to you about this method and its implementation in PDL. So the plan for the talk: model testing in chi-square and how chi-square works. So the first half of the talk is theory. The second half, the implementation in PDL and some live chi-square PDL demos. So model testing in chi-square. So we live in this time of revolutionary discoveries. Higgs boson, gravitational waves. These were not serendipitous discoveries. These were based upon models. We all use model testing in everyday life. We're constantly testing our own personal models of reality. There is in science a commonly used and generally applicable model testing method called chi-square. So by way of motivation, can you use ordinary curve fitting to test your models? Well, here's some actual data. Physics experiment, pendulum, simple pendulum model. The pendulum model is nonlinear, but notice it's been rewritten to be able to be put into linear form, which shows the versatility of the linear model. And it's a simple one-parameter linear model, y equals ax, just a slope. Notice the line is not a best fit line. It's actually the model line. This is the model based upon those parameters, g over 4 pi squared, so we know what those should be. Those points are not individual data points. Those are each a mean from multiple repeated measurements. So there's the model, there's the data. How does the fit to the model look? Well, looks pretty good until you zoom in. And then when you zoom in and see that those error bars are quite far from the model line, the separation of those error bars is a sigma. And if you're more than about 2 sigma, you'd probably reject the model. And notice these are many sigma away. So ordinary curve fitting methods, the problem with them isn't just that they're old, and they are from the 19th century. The problem with them, as we'll see in a moment, is they don't include uncertainties. So ordinary least squares, going back to Legendre, and then when you introduce a linear model, then we call it linear regression, where you take the difference of each point from the line, and you square those, and then you sum them, and you minimize that to get the best model. The problem is they do not include uncertainties. So when people do ordinary model testing, go to Excel or a calculator and they put in the data, they didn't ask for what the uncertainties were. So you can get a best fit, but the best fit may not be a good fit. And the best fit to the data may be a bad fit to the model. So there is a 20th century method that combines both curve fitting and model testing. And that's to minimize chi-square. Now, when you look at chi-square, you'll notice the only thing that looks different, it's still at least squares, it includes uncertainty in the denominator. Now, when you see that, at first thought is, well, it's not that revolutionary. Isn't this just kind of a weighted least squares where you're weighting the contribution of each data point inversely with its uncertainty? The most uncertain point shouldn't count a lot. Well, it is a weighted least squares, but there's a big difference. Ordinary least squares and weighted least squares, they separate the problem of parameter estimation and model testing. They figure out the best parameters, then they use sometimes ad hoc methods for model testing with things like correlation coefficients, f-tests, confidence intervals. Chi-square analysis combines parameter estimation and model testing. It's built from the ground up, terra firma, probability theory, which we'll show, and it's a consistent methodology for answering the important questions we ask of data. What are the best fit parameters? Is the best fit a good fit? What are the uncertainties in the best fit parameters? Should we reject the model? And what about a revised model? Does that represent an improvement? So how does chi-square actually work? It's built upon one main pillar, the central limit theorem. Variables that affect measurements, those include lots of random contributions every time you take a measurement. And we have no idea often what the distribution is of each of those random contributions. It could be a uniform distribution, exponential, who knows? Fortunately, when they combine by a mathematical operation known as convolution. And the result is remarkable, that the distribution of the sum of random variables, and a mean is a sum, tends towards a Gaussian. I didn't see anyone's jaws drop. It's that important, the central limit theorem. That is, it's often considered one of the key concepts in statistics, that no matter what the underlying distributions, when you combine them together, you're going to get a Gaussian, a normal distribution. So the Gaussian distribution can be put in the form of a model. Notice on the lower right, the difference of the data point and a model. That model could be y equals ax plus b, or some nonlinear model. So we can now establish a probabilistic, a sound foundation for this curve fitting and model testing. Paraphrasing JFK's inaugural speech, we should ask not, given the data, how probable is the model, which is what ordinary least squares ask. We should ask, given the model, how probable is the data? This is called maximum likelihood estimation. We draw a Gaussian centered around each data point. What gives us the right? The central limit theorem. Given the model, what's the probability of generating all the data? Well, that's a tall order, that question. So what do you do when you have a problem that's too difficult to solve? You look for a simpler and similar problem. So instead of the probability of generating all the data, how about the probability of generating just one data point? And notice that's given by the Gaussian distribution on top. Then that long line, all that is to get all the data, you just multiply them using the simple rules of probability. If I asked you what are the odds of flipping a coin 3 times and getting 3 heads, it would be a half times a half times a half. You multiply the probabilities. When you do that, then they're going to sum in the exponent. You introduce chi-squared to simplify, and you come up with this remarkably simple result, that given the model, the probability of generating the data is given by e to the minus chi-squared over 2. That means the probability will be greatest of generating the model when chi-square is least. So that's how we do the parameter estimation. You can take a look at it here. You'll notice the top line, or the top graph, is chi-square, which is a quadratic. The bottom graph is the probability or the likelihood function, which is a Gaussian. And the horizontal line is the slope. How do you get the best value for the slope, the parameter a? You find chi-square min, the bottom of the quadratic, and that corresponds to the maximum of the Gaussian, the maximum likelihood that given the model, you will have generated that data. Further, if you look at the graph, you'll see 1 sigma lines on either side of the Gaussian, and then when you go up to chi-square, you see chi-square plus 1 on either side. I wish we had a different arrangement to be able to point out so easier to you on the graph. And these slides, by the way, will all be available on the website along with code. But you'll notice we can get the uncertainties in the best parameter fit as well. So here's a quick summary of what chi-square gives you. You find the minimum chi-square, it gives you the best fit. Second, you can even tell now if the best fit's a good fit, something that ordinary linear regression doesn't do. How do we do that? You'll notice in that little formula underneath, which is chi-square, the difference between the data and the model. What's a good criteria for a good fit? Is if the difference is about 1 sigma. Then do the simple math. Sigma squared over sigma squared is 1. The sum of 1 over all the data is n. In other words, if chi-square min is approximately n, the number of data points, you've got a good fit. Then third, bless you, you can use chi-square min plus 1 to obtain the uncertainties on the best fit parameters. Those are 3 uses. And just like those late night advertisements that say, but wait, there's more. 2 other uses for chi-square. We can now reject the model if the best fit parameter values are significantly, like 2 sigma, away from if we have the luxury of reference parameters, if we know what they should be. And one of the most useful from a both scientific and a pedagogical standpoint in teaching, gauge model improvements by reduction chi-square min. If the criterion for a good fit is chi-square min close to n, then if we revise the model, we get a closer chi-square min to n, we've got an improvement, a better model. So now I'd like to turn to the implementation of chi-square in PDL. Perl Data Language, created by Carl Glazebrook, an astronomer in 1997. He introduced a new data type, a PDL array, denoted by the $ signal to distinguish it from a Perl array. And the PDL arrays, they place PDL in the same league as MATLAB, APL, NumPy, and Python, and other array programming languages. So the chi-square algorithm, to implement it, we need to calculate chi-square for all the parameter values. We need to store the chi-square values in a grid. And then a nice simple way is just to do a direct brute force grid search. The simple grid search works for both linear and nonlinear models, and it avoids the complications of nonlinear minimization algorithms. Computing can be a great equalizer for math skills. One can, with computing, solve problems that would be difficult for a mathematician to solve. So, 2 loopless methods for computing chi-square. If you have a linear model, you can just actually expand the summations in chi-square and obtain chi-square from the summations, and PDL makes it easy to accomplish that by then being able to use the array features of PDL to calculate chi-square over a parameter grid. If you don't have a linear model, but a nonlinear one, then there's additional array gymnastics possible. Now in PDL, it's often called threading, in Python, NumPy called broadcasting, and MATLAB vectorizing, but they're very similar, and one doesn't want to use loops in PDL. Here's an example of this, which in loops, it's sometimes easy to see what's being done when written in for loops. You can see it's a triple nested for loop where you first have in the inner for loop the going through the data, then after that the first parameter and then the second parameter, but very, very, very slow. So you can use instead PDL's array features to calculate chi-square grid, and this is just one way to accomplish that, reshaping the data, then calculating chi-square, and essentially you'll notice under calculating chi-square is essentially going through the process of the definition of chi-square, but it's able to deal with entire arrays at one time. So I'd like to turn to some demos of PDL chi-square scripts using Strawberry Perl with PDL as a portable application, which makes it very convenient, just installing that and having it be a directory on the desktop. So I'd like to begin by looking at a simple, actually I think first I'll just show what the data is. So we've got 3 arrays with data, an X, a Y, and a Y error. So there's error only in the vertical direction. And we're going to try to model that first with a single parameter, Y equals AX linear model. So we're going to run the first script, and we're using here for the plotting David Merton's fine module on PDL graphics Prima Simple, which has some really, really nice and useful features. And this is just showing the data. Now, the script itself is telling us a couple of things. It's telling us chi-square min is 44, but the number of data points is 20. Well, it's of the order, but not quite. We could do better. So it's not outrageous, but we could get a better model perhaps. And it's giving us the best fit parameter. Let's see how that looks. I'm going to close this, and now this is the actual graph of chi-square versus the slope. And one of the nice features of David's module, this in Prima, we're able to move this around, so be able to see interactively where the min is. So remember just how this works. So chi-square min is getting us the best value of the parameter, and then if we went chi-square min plus 1 on either side, that gives us the uncertainty. Then if chi-square min is of the order of n, we've got a good fit, and then if we had some real parameter references, we'd be able to check to see whether or not the model should be rejected, and we can now see whether or not we can get a model improvement. So let's try a model improvement. We're now going to go to a 2-parameter model, which is y equals ax. And again, that's just the data plot, so that should look the same. But first I want to show you the reported results. Chi-square min, which was 44 before, now it's 16.2. Closer to 20, the number of data points. We've got an improvement, and we can gauge it by the value of chi-square min. And we've got best fit parameter values for A and B. Also, it's reporting A and B index because I'm having it search through a parameter range of 100 values, and if it were off to one side, we'd have to adjust that range. It's kind of a manual process to do the parameter search. Now I'm going to close this and take a look at the chi-square plot. Now for the chi-square plot, I'm using a new plot, GNU plot, and for the contours, and you'll notice, so we've got contours. How come? Well, with one-dimensional model, chi-square was a quadratic, a parabola. If you have a two-dimensional model, so you have parameter A and parameter B, that quadratic and parabola is now a paraboloid. And its minimum is centered right on the best value of A and B in the parameter plane. So that's what it's showing. It's showing right here is the best parameter value. And what I've drawn here, these are the 1 and 2 sigma contour lines. So if we now have an actual parameter parameter reference value, and if it's out here, we know that the best fit value, which is in the middle of the ellipse, is more than 2 sigma away from the reference values, and we would reject the model. So that's something that's available by doing the chi-square analysis with contours. And then I'd just like to go to the last couple pages here. Acknowledgements. I want to acknowledge a colleague, spoke of Keith Zengel, for making some helpful comments, slides, and his work of chi-square. David Mertens for some of the documentation that's helped me in the last couple months learn PDL and Perl. Forgive me, newcomer to this all, and I'm looking forward to David's talk in a couple of days on writing computational software in good manner. And Chris Marshall for PDL, which using in the Strawberry Perl environment, and also Carl Glazberg creating Perl, PDL, and of course Mr. Wall for Perl itself. So I'd be happy to take any questions.
I'm sorry, I can't remember the term for it, but the thing that meant that the random errors result ultimately in a Gaussian distribution?
Yes, the central limit theorem.
Central limit theorem.
Yes.
Actually, by the way, speaking as the recorder, if you wouldn't mind taking questions from the microphone,
of course,
we'll hear you better.
Yes.
Record you better, that is. So, my jaw was dropping. I don't know anything about statistics, but law of averages over averages?
It's a great question. In terms of first it being a law, the mathematicians think it's a law of nature, and the physicists think it's a mathematical fact, and it turns out it's a little bit of both. It's actually by this mathematical operation of convolution, which is so central to so much of the practical application of mathematics to physical systems, it ends up smoothing the distributions, and when it's done over and over again, you end up with this Gaussian distribution. It may very well be that the phrase you use might be applicable. I'm just not sure if so I'll hesitate to say, but that might turn out to be the equivalent. Yeah, thank you.
Like a multiple tossing of like two or more dice, you eventually arrive.
Yeah, and thank you for mentioning that. There are ways to get a Gaussian separate from the central limit theorem. If I handed you all a sheet of paper and asked you to measure the length of the side, we'll get a Gaussian. Why? Because if you have a large number of independent measurements, each one with a random contribution, and the random contribution is small, if those four criteria are met, you get a Gaussian. But that turns out to be separate from the central limit theorem, which says that no matter what the underlying distributions are, when you sum those together through convolution, you will always get a Gaussian. Yes, Dave?
It's always a Gaussian. It's enough time in like engineering or math, it's always a Gaussian. So that's why my jaw was not dropping. It's always a Gaussian.
Yeah,
That's a binomial distribution.
Right.
It becomes a Gaussian.
Yeah. There are important non-Gaussian distributions, like the distribution of size of asteroids is not Gaussian. There's a large number of little asteroids and a medium number of middle size and very few large, and that kind of power law fractal distribution is very common. But for physical measurements, yes, when they combine together. David?
I was curious, you mentioned that you'd rather just scan over a set of space of parameters rather than using nonlinear methods. Like, I was thinking Leavenworth Markov, which is one way to kind of look for the basic, right? Have you had experience trying to use that and having
No, thank you for asking. In fact, that technique is used in CERN's software, Minuet, which is part of their root software that they use. And it's just because we use chi-square in an educational setting where we're having students work actually with the programming that try to keep the search method very simple. And the fact that that one method can be used for both linear and nonlinear. So it's mainly for that reason. But yes, a lot of the professional applications, they do use it, and that method is remarkably robust. Yes. Okay, well, thank you again.